So for the linear regression model, we have a lot of choices as it comes to the specification. I can specify a linear model that's linear in data, or I can specify a linear regression model that's nonlinear in data in many different ways, for example, by adding quadratic terms or by considering various log models. So if I do specify my model as a linear model, linear in data that is, then I would like some kind of confirmation that this linear model adequately captures the data that I observe. And one way to do that is through Ramsey's reset test. So let's say I have two explanatory variables, and in that case I can just specify a linear regression model which is linear in data like this. But we also know that if the true relationship between the x variables and the y variable is non-linear, then this model will not fit the data particularly well. So I have a bunch of other alternatives here. I could, for example, consider a log-log model like this, where I have logged my x variables and my y variables, or I could consider a log linear model, or I could even do a model where I add quadratic and interaction terms, such as this one, where I have my linear part here, I have quadratic terms, and I have an interaction term. Now, by far, the most common specification in econometrics is the linear one. It's the easiest one to estimate, and it's also the one that easily allows us interpretations of the beta parameters as marginal effects. However, if you do make this specification, then it would be nice to know that it reasonably reflects the data. So the Ramsey reset test is designed to detect misspecifications like this. If this is, for example, the true data generating process, if the true data generating process is this one with quadratic terms and interaction terms, then our model is what we say misspecified. It is not the correct specification. And the Ramsey reset test is a general test of misspecification. It simply tests if our linear regression model, which is linear in data, is misspecified. So let's move on to the question of how this is done. And the idea is actually really straightforward. So you have a linear regression model, then you can perform this Ramsey reset test, where reset is just short for regression equation specification error test. So it's meant to test a potential error in your specification of your regression equation. So you start with a linear regression model that you estimate. Once you have estimated the model, that is estimated all the beta parameters, you can calculate all the fitted values. So you can calculate all yi hats. Now take all these fitted values and square them one by one. Then you run a new regression. And your new regression is supposed to be exactly the same as the one you started with, but you add one more explanatory variable, and that variable is the square of the fitted values. So you're supposed to add this to your LRM and re-estimate it like this. So let's call that the parameter in front of the squared fitted values, we can call that gamma. And here's the result, which we won't really cover in that depth in this lecture. But you can show that if your regression model is correctly specified, that is, if the third bullet point is the actual data generating process, then the square of the fitted values will not be able to help you explain yi. All the information is then in the explanatory variables, so the fitted values is not going to help you. And that means that if your model is correctly specified, gamma in this new regression model is 0. On the other hand, if the model in bullet point 3 is misspecified, so you've actually estimated a model which is not consistent with the data generating process. Say, for example, that the true data generating process should have logs of all the x variables or something else. Well, no matter what the misspecification is, if that's the case, then squares of fitted values will actually improve the fit. So for a misspecified model, gamma will be different from 0. So to review, gamma is equal to 0, your model is correctly specified. Gamma is different from 0, your model is not correctly specified. So Ramsey's reset test then simply tells us to test if gamma is 0 or not. So we simply perform this test of the null hypothesis, gamma is equal to 0. We know how to do that, we can just do a t-test. And the idea here is that if you reject this null hypothesis, you have signs of misspecification. Particularly, you have signs of non-linearity in the data. The rejection is not going to tell you exactly what this misspecification is. It's just going to tell you that it's likely there. So this is a very popular test in econometrics to do, and for this reason it has been programmed into most econometrics software. So typically you don't have to carry out this test manually. That is, you don't have to go through this process of saving the fitted values, squaring them, doing this new regression. The software will do it for you. Have a look at Gretel, for example. So let's say I specify a model which is linear in data, and my model is that final is explained by SATV, SATM, and HSGPA, like this. I'm uncertain whether this is a correct specification. I'm suspicious that there might be some non-linearity in my data, so I decide to perform a reset test. Then just go to test, go to Ramsey's reset, and click on the squares. OK, and you can see that it has done this new regression model for us. It has used final as our y variable. It has the same variables as the previous one, SATV, SATM, HSGPA, but it has also added y hat squared, y hat being fitted values. So all we have to do to test for misspecification is to test if this number is significantly different from 0. And that's easy. We can do a t-test, so we can do this, compare that to a critical value, or even quicker. Just look at the p-value, and this p-value is very large, greater than on pretty much any level of significance that we can work with. So in this case, we should not reject the null that gamma is 0. And that means that I do not find any signs of non-linearities or misspecification, at least using the Ramsey reset test. EViews, equally simple. Just do quick estimate equation. You do final C SATV, SATM, HSGPA. Then you go to View, residual diagnostics, it's not, it's stability diagnostics, Ramsey's reset test, and number of fitted terms, you just do 1. And if you go down a little bit, you have exact the same regression here, where the square of the fitted values has been added, same p-value, do not reject the null, no signs of misspecification. You can also, you don't have to scroll all the way down, you can find the same p-value right there. Some authors would also recommend trying to add higher order polynomials of fitted values. That is not just the square of the fitted values, but perhaps also the fitted values cubed. And that's an extension that you could consider. So you could add cubed values to the regression as well. That's actually the default in Gretel. If you go to test, Ramsey reset, it has squares and cubes. And in this case, you add both the squares and the cubes. And the null hypothesis in this case is that these are both 0. So that's a null hypothesis with 2 restrictions, and it must be carried out using an f-test. A t-test can only handle 1 restriction. So in this case, these p-values are not interesting. The interesting value is this one, the p-value of the f-test. But again, we draw the same conclusion, no signs of misspecification. And you do the same thing in eViews by just putting a 2 in the number of fitted terms here. Put 2 here, then you also get an f-test, a p-value for the f-test, and add it like this. If you're wondering why fitted values themselves are not included, that is without the square, the answer is simply that by construction of OLS, the parameter in front of fitted will always be 0, no matter if it's misspecified or not.